Get ready. Y down feed, now.
Hello and welcome back to the Tin Barn. I'm Pragmatic Lee, and once again I'm standing over here next to my Harig surface grinder. As I've said in previous videos, and if you follow this channel, you know I've done several videos on this surface grinder project of trying to automate or CNC the X-axis on it. And I've run into a lot of difficulties, a lot of hurdles on this, but hopefully I've overcome them all. And the purpose of this video today is to kind of draw this to a conclusion. Was it a success or a failure? In my book, I'm going to call it a success. There's been a lot of hurdles I had to overcome on this, most of which I've documented in previous videos, but I want to, as I say, draw this to a conclusion. As I said earlier, this series of videos has not been getting near the number of views I would like for them to have got, nor is it getting the number of views that other videos on my channel get. But as I've said as well, there's been more comments, and there seems to be the fact that the people that are watching these videos are really interested in it. And I want to kind of do this as a recap to this project to draw that to a conclusion for those of you that are really interested in it. Now, before I get into what I have done to the surface grinder and what I've set up, what I've programmed, I want to give you a short little video clip of a segment that one of my viewers sent me. Roger Cox sent me this video clip almost 3 months ago. He's one of the viewers on the channel, and he sent me this clip, and it really got the gears turning. Take a look at this. It's a short clip. Take a look at it right quick. I touched base with Roger a couple times after he sent me that email with that in it, and asked him if he didn't mind, please share with me a list of the components that he used, and also to share with me the code that he had put together. Now, he told me right off the bat, and I understand. He said, I'm not a programmer. This is some kind of hacked together code. And he pointed out as well to me in one of the email responses that he was having trouble with what he thought was slippage. Now, if you recall from one of my previous videos, I thought I was having that same issue on the X-axis where I would go X number of steps in one direction and go the same number of steps in the other direction, but it was not coming back to the same point. And several viewers pointed out to me the problem was that I was missing steps, losing steps. When I would start out, I was starting out at full speed. It's kind of like spinning your tires. The motor was trying to go, but the table, this heavy table and vise, was not moving. And when it got to the end of that and started back in the other direction, I was losing steps as well. When it got ready to stop, it was putting on brakes, but it was sliding. The table was still moving, but there was no steps being counted on the motor. So that might have been, Roger, if you're watching this video, that might be your issue on that. What my solution and what the viewers, several viewers recommended, was that I ramp up the speed. Instead of starting out at full speed, start out and ramp up to that full speed, and then instead of just putting on the brakes and stopping, ramp down. And so that's what I wound up doing, and I talked about that in a previous video on this project. But Roger had 4 major components in addition to his surface grinder itself. He had the stepper motor. He had a stepper motor driver. He had a stepper motor or a power supply for that driver. And Roger was using the Arduino, which is a controller, device controller, microcontroller. My interest in this was to see if I could do it with the same 3 of the same components: the stepper motor driver, and the power supply for the driver. But instead of an Arduino, I wanted to use a Raspberry Pi. A Raspberry Pi, as I've said before, is a full-fledged computer. It is about the size of a pack of cigarettes. It is ideal for running numerous different applications. I have one here in the tin barn that I've been using probably for at least 6 years now. That is my file server. It's a Samba file server. Again, little bitty thing sitting on the shelf over here. It's where all my backups go. It's where a centralized file server. I also have them running the Pi Zeros, a little small version of it. I have several of them running security cameras around. The Raspberry Pi can be programmed with the Python programming language, which I used in my career as a programmer. Probably the last 6 or 7 years of that career was using the Python language. The Arduino uses a hybrid of the C# language. And even though I've programmed in C during my 35 plus years of a programming career, I programmed in C, just plain vanilla C some, but it's been many, many years ago, and I'll be 72 later this week. And I'm really not interested in learning a new language. So let me reposition the camera right quick and show you the components in my setup. Now, Roger was using 1 stepper motor and 1 stepper motor driver, and he was controlling the x-axis. My final version of this project is controlling the x and the z-axis. The z-axis is the axis that runs perpendicular with the spindle, just like on your lathe. You've got the spindle over here, and as you're going into it, that's the z-axis. On a mill, your spindle goes up and down, and that's your z-axis as well. So again, let me reposition the camera and show you the difference in my setup and in what Roger had. Now on the shelf up here, I've got a mouse, keyboard, and a monitor. This is an old Samsung monitor that come off a computer. I don't know where. Really have no idea where it came from. But it was it did take the HDMI input, so it got used on this project. The wallpaper that I'm using on this, or the image that I'm using for a wallpaper, is an image of the Grand Canyon. And the reason I chose that was the week that I finished this project, or what I'm calling finished for now, was the 4-year anniversary of my wife and I going back to Arizona and visiting the Grand Canyon. When we got married, we drove a 67 Volkswagen Beetle from eastern North Carolina, near about all the way across country to Tucson, Arizona, and set up housekeeping out of the back of that Volkswagen. We were newlyweds. And the whole time we were stationed out there in Tucson, we talked about, well, when I get discharged, we're going to go up to northern Arizona and see the Grand Canyon. Well, I got discharged on Thursday. We got in the car and we headed back to North Carolina, and by Saturday morning, with an 18-month-old baby, we were sitting back in North Carolina. But anyhow, that was that's the purpose of that background screen. Down here are the components for my setup. As I said, Roger had a stepper motor. Let me pull over here right quick. mounted to the surface grinder itself, and I'll go in much more detail on these mounts a little bit later in the video. But the stepper motor, this is the NEMA 23 that I'm using for the X-axis. You may recall on a surface grinder you got a large wheel over here to move the X-axis back and forth. The other stepper motor is a smaller one, a NEMA 17, and it's used to control the Z-axis going back and forth. So I've got two stepper motors, where in Roger's setup he only had one for the X-axis. And here are the various components. We saw the two stepper motors. The stepper motor driver are these devices right here. It's a DM542T digital stepper driver. There's one for the large NEMA 23 stepper motor, and there's another one for the smaller NEMA 17. The only difference in the setup on these two is a set of dip switches up here that you configure based on the amperage. That NEMA 23 is a 4 amp. So that's what this is set to. The NEMA 17 is a 2 amp. So the dip switches are set up for 2 amp. Now the power supply, this is a 48 volt DC power supply that simply powers these two drivers. They could be powered anywhere from 18 volts to 50 volts. I chose a 48 volt power supply for each of the two. In Roger's setup, he only had one of these. This power supply would power numerous ones of these. I have two. Now, he used the Arduino, and I showed you a picture of one of them just a minute ago. I'm using a Raspberry Pi. This is the Raspberry Pi right here. It is a full-fledged computer, power switch for it on and off. But you can see there's a series of wires coming out of these. These are what's called GPIO, general purpose input output. So a stepper motor has two sets of windings. One set of windings is to determine what direction the stepper motor turns in. That would be direction plus and minus up here. And again, I showed all this wiring diagram in an earlier video. But the other set of pins is the pulse pins. And the way a stepper motor works is you don't just send it voltage and it goes in a direction in a reverse polarity and it goes in the other direction like a DC motor. A stepper motor, you send it a pulse, a high, low. A combination of a high and low is a pulse. And each time that it receives a pulse, it does one step. In the situation of my stepper motors, each one of them takes 200 pulses per revolution. So what we have down here again is the power supply, the two drivers, and the Raspberry Pi. Okay, let's take a quick look at what I did to the front of the surface grinder to mount the stepper motors. I'm sure, again, if you're familiar with a stepper or with a surface grinder, you realize that over here on this side there was this large wheel that was used to move the table back and forth. Of course, I removed that wheel. I put the sprocket ratio is 1 to 3. This is a 20 tooth and this is a 60 tooth. And I used a 3mm pitch belts, 10 millimeter wide. But this is simply a piece of angle iron right here that I cut out to fit the vertical part up against the housing here. In the housing, I drilled and tapped a couple 1/4-20 holes, and the way this belt is tensioned on here is to loosen these two 1/4-20 bolts that's under here and slide this mount back and forth. This end of the mount is actually resting on the housing of the surface grinder. So that takes care if I need to do a manual movement of the X-axis on the table. Now this switch right here controls, you remember I showed you that 48 volt power supply. This switch controls the power going to that power supply. If it's active, one of the things about a stepper motor is that when power is applied to it, it's pretty much locked. It holds its position, unlike a DC motor or even an AC motor. Once power is removed, you can freely move, the motor freely turns. This originally was just simply a toggle switch, but I decided I will go with this panic type switch simply because if anything goes wrong, I can simply hit that switch and everything stops. But it also gives me a simple way of turning power off the driver power supply so that I can move. Over here is the NEMA 17. It is sitting on a piece of angle iron as well. The difference here is the way I adjust tension on the belt here is vertically loosen these two bolts right here and vertically move it up and down. Now I made a little small handle here to replace the Z-axis handle wheel that was on there. X-axis on this particular model of the Harig Super 612, the X-axis is a cable. It is not a rack and pinion gear or worm gear like this is. It is actually a cable, so there's no backlash whatsoever. It's a spindle holding a cable that's mounted over here, and over here on this end is just an idler, so there's zero backlash. However, on the Z-axis here, moving in and out, there is, I measured it before I took this wheel off, which has a graduated dial on it. I determined that there was 30 thousandths of backlash in this 50-year-old machine. So that's something my program that steps the Z-axis has to account for. If I'm going in this direction, moving the table in, and I get ready to bring the table back out, there's 30 thousandths of movement here before the table actually engages and starts moving. So that had to be kept in mind as well. And I simply made some handles here with some shoulder bolts and a handle to make it easier to turn. Now on this over here is also a 1 to 3, 20 tooth to 60 tooth, but instead of the 3 millimeter pitch, this is like a 2 millimeter pitch. And right now all I've got is a 6 millimeter wide belt. I do have a 10 millimeter wide that'll fit these pulleys on the way. And I will say that if you ever decide to do a project like that, one of your hardest things to do is going to be getting these pulleys. It took over a month ordering them from either Amazon or eBay. I've got a drawer full of these pulleys, not a drawer full, but I got 8 or 10 extra pulleys now trying to find the right combinations. And every time I would order something, it would literally take a month to get them. They were coming from China. So keep that in mind. In one of my previous comments, there was videos, there was a comment about a local or a stateside supplier. So check the comments out in one of the previous videos. But now let's look at the program that actually controls this. And remember what that program needs to do is on my chuck right here, this is simply a piece of masking tape, but I put it on there and marked the center of it. And then when I lay a piece of material up here, if it comes to 2, then I need to set my X travel to that 2-inch plus enough extra for the wheel to get off the workpiece, and also to do that ramping up and ramping down. A rule of thumb of what I've come up with the code that I wrote is if I got a 4-inch piece here, I need to tell it X travel 6 inches. That gives it 1 inch on each end of the workpiece to either ramp down or ramp up. So when we put a workpiece for this type project, we're going to put it up there and center it up. Now, a mag chuck has lines in there, and with this little scale that I've put in, I can see the segment line for the 4-inch, and simply get that centered in between those marks. Then I know, okay, this is a 4-inch. I need to, well, this is showing on the 4-inch mark here, a little less than 4 inches actually. Then I probably need to go a 5 to 5 3/4 inch throw back and forth. Again, I want to give this wheel, I want there to be enough travel so that the table has time to slow down after it's off the workpiece and time to speed back up before it gets back on the workpiece. Now we'll mag that down for right now. All right, now let's go over and look at the program. I'm not going to show any code in this program. I'm just going to show you the final result that I came up with. Okay, now we're looking at the computer monitor now, and again, as I said before, an Arduino is a microcontroller, and I am not knocking Arduinos not one bit. They have an absolute definitive place in the world of automation and controlling devices. I wanted to use a Raspberry Pi simply because I was familiar with them. I'd used them before. However, this is my very first project of ever trying to control even as much as a light bulb with a computer. This is the monitor, and again, it's a full-fledged computer. I could go up here and surf the web on it if I want to. It's got a full menu of programming, internet, sound and video, graphics, run, shut down, so forth. And I've got several programs on it. But the one we're interested in today is the one that I wrote for this surface grinder automation. Now let me see if I can zoom in a little bit on that, so hopefully you can see what buttons I'm pushing or what values I'm putting in. All right, here's the interface that I wrote in the Python programming language using the tk-enter GUI library. But it has several inputs here. One is the X travel. That is how far the table moves left to right. Now again, if I've got a 4-inch piece of material on there, it's centered on the mag chuck, I probably want to go 5 inches here. Z travel is how much the table goes in and out. Now what that should be is if you have a let's say you would line up your workpiece, or you would line up the wheel right at the edge of your workpiece. Then whatever the width of the workpiece, in this case that little piece I put up there was 2 inches. Now we want 2 inches plus the width of the wheel. So 2.5 inches, because we want that wheel to come completely off the front edge. We're going to start at the back edge of the workpiece, and we want it to come completely off the front edge. So 1/2 inch wheel, 2 inch piece, I'm going to add just a little bit of that, 2.75. Worst case, is that it'll make a couple passes and not be on the workpiece, which is again perfectly fine. Now the Z step is how far, when we get to the end of that X travel, how far do we want to move in, come back across the X travel. Now how far do we want to move in and go back? The wheel that was for the Z travel of going in and out, one complete revolution was 200 thousandths. I found over my years of using this step grinder or surface grinder, for rough finishing, half a revolution, 100 thousandths, was plenty fine. Did not put an overload on the wheel and was taking a good step. Now I want to go, so I'm going to default that to the 100 thousandths, half a revolution. The speed, I set up two speeds on this, a roughing and a finishing. And all that is how far or how fast do I move that table back and forth under the stone. And this speed takes into consideration the wrapping up, the working across the material, and wrapping down. Wrap up, across the material, wrap down. So I come up with two values on that. Now these two orange blocks down here will give us the status of what the program is actually doing, or what it's telling the surface grinder to do. It'll normally say one of two things: X-axis, or grinding X, or advancing Y. Now other things it might say is the status is that it's paused or a stop was detected. Now the progress on this is the progress of the Z stepping. We're going to step in. We said our workpiece was 2.75 of Z travel, and we want to step 100 thousandths at a time. So 2.75 divided by 100 thousandths is going to tell us how many steps we need to go. Now progress, it'll be good to know how many of them when we're getting to the end of those steps, because at the end of that step we need to manually reach up there and move the y-axis down. In my case, I usually go 100 thousandths, 200 thousandths, and occasionally if I'm doing a real rough finishing, I'll just go 300 thousandths down. I think you'll see all this. It'll make more sense to you in a minute. But this progress bar down here, progress status, will tell us, like if we have 10 steps to make, step 1 of 10, 2 of 10, 3 of 10. So that will warn us to get ready to do our y-axis down feed. Now we've got 4 buttons over here: a go, a pause, a stop, and an exit. The go button says take these values, verify them, that the X travel is within a certain range. I've set up a range. My chuck is 12-inch chuck plus a little bit off of each end. This will not take a value greater than 12.5. It will not take a value less than 3. That was what I chose. Z travel is 6 inches wide with a little hangover off each side. So the maximum it would take is 6.5 inches. The minimum it would take, I said, was 1 inch. That's basically a 1/2 inch piece with a 1/2 inch wheel. The Z step needs to be between 0.025, a quarter of a revolution, or an eighth of a revolution, up to 200 thousandths. I'm not going to try to step over more than half the width of the wheel at the time. And these two are either of these two choices. So the go will evaluate all these choices. If they're valid, it will actually start going. At this point, I could exit out of the program. But once I hit the go button will be disabled, and the exit button will be disabled. The only thing I can do is pause the program or stop it. Now, why pause it? Well, pausing stops the program right where it is at the end of a cycle. A cycle being, or a round being, the end of the x-axis, it would stop, x travel. Or if it starts it, its way back and you click the pause or the stop, it's going to finish that cycle. Finish that round and get to the end before it actually pauses. Now I do not have the power turned on to the power supply down here, nor do I have the grinder spinning. But the program is still going to run, and it's still sending signals out to these drivers down here. But the drivers aren't turned on, so nothing's going to happen. But watch when I press go here. It'll prompt and say, is the table in the correct position? Meaning, am I on the back right corner? That's where I want to start. I travel and the table move in. So I say yes. Now it says it's grinding X, advancing Z. Grinding X, advancing Z. And notice down here, it is counting up. I'll let that count and bring you right back when it gets a little bit closer. Now I will say these 28 steps right here, that was the 2.75 divided by 0.1, which gives 27.5. It rounds up. That's 28 steps on the Z that it's going to move before it's time to stop and start back in the other direction. And one of the things it'll do when it starts back in that other direction is account for that 30 thousandths of backlash in that handle. You'll see all that in just a minute. But I want you to listen to the program as well here. When it gets to 27 or 28, in this case, it'll tell me to get ready. And then when it gets to 28 or 28, it'll say advanced or Y feed down. Notice the pause and the stop are active buttons now, but the exit and the go are grayed out.
Get ready.
Just told me to get ready.
Y down feed now.
So that's when I would go down on the down feed. Now the way the pause works, again, it got to the end of that round, the end of that cycle, and it shows us the status is paused. The progress is at 2 of 28. Now, the only thing I can do right now, I can't go, I can't stop, I can't exit, but I can resume. And we know all GUI programs on Windows, Linux, or whatever has this little X button in the top right-hand corner. Well, what if I was to hit that? It tells me to use the exit button after stopping the process. In other words, I'm trapping this right here and not letting it stop at a bad time. If something's going wrong, if I forgot to engage the mag chuck or whatever, I can hit that panic button and everything's going to stop. Except the program. The program's going to keep thinking it's going, but everything mechanically is going to end. So I hit the stop button here. It detected the stop, and it says the cleanup is done. One thing about the Raspberry Pi and the GPIO pins is that you need to run this cleanup routine at the end. Don't you leave them in an orphan state, and they don't know whether the program, when it starts back up, will not know if that pin is already high or is it low. Is it in its normal state or is it in no state? That cleanup takes care of all of that. All right, so let's exit that out. But remember now, we're going to put these values in. Actually, I can let this set right here. Let's go. Let me move the camera around so that you can see what's happening on the surface grinder. All right, you're looking at the surface grinder now. I'm going to move this over manually. Advance the Z in. And I'm just going to manually get that to where it's just touching now. So I'm going to move to the back side, and remember, it's going to start turning in, so I want to take any backlash out. And I'm going to start this at the top. I'm going to move this off the edge. Remember, that's just inside. That's at about the 3.5. So if I want an inch on this end and an inch on that end, I'm going to set it up for 5, for a travel of 5. Now, I will turn on the spindle, release this so that power's on. Now up here, I set X-axis, look in your top right hand corner of your screen, back over here on the program, 5 inches of X travel. 2.75 of Y travel. Let me turn that back off right quick and show you another little thing I come up with. This is simply a hook rule. It was an aluminum rule I had laying around. I put me a hook on the end of it. Now, obviously without the spindle running, I can hook that on there. Back side of this wheel I want to come and clear, so it says 2.35 will get that wheel off. So up here, again, in your upper right hand corner of your screen, I have that set at 2.75, and I have the Z step at 100 thousandths, which means this is going to turn a half a revolution. Something I failed to mention earlier, a lot of this program has to do with calculating the math. Now, before I ever took the original wheels off, as I said over here, I determined there was 30 thousandths of backlash in this wheel. But I also was able, because of the dial on the wheel, to know that one complete revolution was 200 thousandths. So 200 thousandths here, how does that equate to a number of steps up here? That's where the math come in. All right, this is a 3-to-1 ratio. So I had to determine how many steps, 200 steps per revolution, how many revolutions does this need to turn this a half a revolution. See, these programs don't come out of a can, folks. You gotta do the math and figure them out. Over here, I determined that one revolution of this handle, the original handle up here, one revolution of it moved this table exactly 4 inches. That may vary with other surface grinders, but one revolution of this moved the table 4 inches. One revolution here moved the table 200 thousandths. A lot of difference. So I had to come to the math to, if I wanted to move this 6 inches, how many steps at 200 steps per revolution, how many steps do I need to make a revolution, 200, how many revolutions do I need at a 3-to-1 ratio to make this go 4 inches, 6 inches, or 8 inches. Again, a lot of math involved in that. So we're set up for 100 thousandths step in, and we're set at speed of roughing. Let's go. Is the table in the correct position? Again, back right hand corner is where I want to start. We'll say yes. Now it should just barely touch this time around. It's not even quite got up to the piece of material yet. I always like to be conservative on this first pass and not put too much pressure on it to begin with. When it gets close to this end down here, see, I'm just barely getting a spark now. when it tells me to get ready in a second, I'm going to get my hand up here on the down feed and get it ready to actually down feed a couple of thousandths. I'll try to get the camera set up to where maybe you can see me doing that as well. Notice this is going a half a turn, which is 100 thousandths. It's going to tell me in a minute to down feed. I'm going to down feed, in this case, 2 thousandths, but make special note of how this handle moves. It will take up that 30 thousandths of backlash.
Get ready. Y down feed, now.
Notice that little bit of movement there? Now it's not at the top or at the bottom because it made up for that 30 thousandths of backlash. Now when it gets to the back side this time, it's going to make up for that 30 thousandths in the other direction, and you're going to see this handle back to a vertical, either top or bottom position. Again, I think you see what's happening. When the X gets to the end of its cycle, then the Z advances. And that's the same thing we will be seeing over here on the status and progress line of the program. Grinding X, advancing Z now. Advancing Z, grinding X. And this down here is telling us that we're going to do 28 steps on the Z-axis, and right now we're on 17 of them. 18 of them headed back this way. Now I'm going to advance it down just a thousandth at the end. Now if I wanted to pause, I just hit the pause button over there. Everything dealing with the Raspberry Pi and the program and the stepper motors has stopped. It did not stop on top of our workpiece though. We don't want to dwell on a workpiece. It finished that cycle to the end. Alright, I will resume. And it should be just working off the edge of our piece now. Again, watch it take care. Watch it take care of the backlash.
Y down feed, now.
See that little bit to come back up? And now we're back at that starting position. Now I'm going to stop the program. And again, it will not stop on top of the workpiece. The only way it stops on the top of the workpiece is if you hit the panic button. So I've stopped it now. Now I'm going to back off a little bit. I have to take power off, back it off just a little bit, get rid of my backlash, and I want to start from this end down here. Alright, over here on the program, remember on that X speed we had two values, either roughing or finishing. I'm going to change that to finishing. This right here, I'm going to change it from roughing to finishing. And now instead of stepping over 100 thousandths, I'm going to step over, or stepping over 100 thousandths, I'm going to step over 50 thousandths. I had to get that in my mind. All right. So I've changed the speed, and I've also changed the Y-axis, or I'm sorry, the Z-axis step over. So what you will see now, instead of this making a half a turn, it will only make a quarter of a turn, which is 50 thousandths. And up here on the dial, I'm only going to come down 1/2 thousandth. So 3 things have changed here. Number 1, up here, I've only stepped down 1/2 thousandth instead of a full thousandth or 2 thousandths or 3 thousandths, whatever I was doing. The speed that the table is moving, I've slowed it down considerably, about 30% in the code. And then thirdly, instead of stepping over 100 thousandths, I'm only going to step over 50 thousandths. So over here, I'll hit the go again. Need to turn power back on to the drivers. Table in the correct position. You should see the table moving considerably slower now. And we don't have near the spark we had before because we're only down 1/2 thousandth. Over here, instead of it having 28,000 or 28 steps, where we divided 2.75 by 100 thousandths, it's got 55 now, which is 2.75 divided by 0.05 and rounded up, of course. Alright, at the end of this Z-axis cycle, meaning the table has worked all the way off, which it has already, but again it's going to give me the warning or give me the notice to get ready to step down on a Y. But on this last half of the finishing pass, I'm not going to let it, or I'm not going to advance the Y down. I'm going to let it spark out.
Y down feed now.
Alright, I did not down feed it any, but I'll let it feed all the way back across. Again, this only going 1/4 of a turn at a time, just for spark out. A lot of times on the spark out run, spark out pass, you'll see in some instances more sparks than you do in other instances. And the majority of the time, that's simply where some of the metal filings.
Y down feed now.
But that's simply where some of the metal filings are setting on the piece and the wheel has hit them. Now it told me to get ready, and I knew this was going to be the end of the cycle, so I went ahead and hit the stop button over here. So when it finished that pass, it stopped all table movement.
Goodbye.
And I just exited the program over here and it told me goodbye. Pretty much got a mirror image on our piece here. I'm very pleased with the finish on that final. Don't know whether you can see it or not, but this was one of the roughing passes, and you can see considerable difference in the two. Okay, I think I'm going to probably call this project completed for now anyhow. There may be some other things I do later to the program. I'm going to keep using it. If I find any issues with it, I'll try to correct them, or if I find any enhancements, I'll try to correct them as well. The only thing I know that I do want to do, and I'll probably do a video on that, but I want to put some shields over these motors. Stepper motors are sealed, so I'm not concerned about getting iron filings in them. However, they do get hot. Now, it's kind of uncomfortable to hold my hand on that. But I have run this setup for an hour, hour and a half at the time, grinding large pieces. I've used this considerably since I finished this project. And these motors get hot. By design, they get hot. I measured these, this with a temp gun thermometer, and it got up to between 145 and 150 degrees Fahrenheit on the NEMA 23. On the NEMA 17, which is just making the little short steps, it got up to about 125 to 130. So while that won't blister you, it's uncomfortable if you should happen to put your hand on it. So I'm probably going to make some shields. In my mounts, I actually drilled and tapped some holes in this one to make a shield to come up and go over, and a little bit of belt protection as well. Keep your fingers out of the belt. Same thing for this. When I made this mount, I put some holes in the side, drilled and tapped some holes that hopefully I can build a mount to go over, and again to protect this belt to a degree, or protect the user from putting their finger in the belt to a certain degree over here. Again, I'd like to thank Roger for the inspiration of this project. As I said, I've never done anything like this before. I've wrote code for 35 years as a career, but none of it ever involved controlling external devices like this. This has been, as I think I've said in a previous video, this has been one of the most frustrating yet rewarding projects that I think I've ever done out here in the tin barn. There was a lot of frustration, interference from the VFD up here, interference from electrical currents, just all kinds of issues that I didn't foresee. But I have enjoyed overcoming them. They don't call me pragmatic for no reason at all. I'll tell you the story of that one day, of how I got the name pragmatic. But for now, I just hope you enjoyed this video. Hope you've enjoyed this series. Maybe got a little bit out of it. Take care, and I'll see you on the next video.